what you're looking at here is one of the earliest spacecraft to go into space. It's called the Sputnik 2. And the Sputnik 2 was launched in 1957 by the Russians, and they put this dog inside it, called Lucky. I think so.
Can we make sure? Because I don't want to be like sad the rest of the day.
I'm pretty sure.
I want to like be
he made it into
definitely
space,
sad.
and I think he just died up there. I'm not sure.
Yeah, that's a good question. I don't know.
Yeah,
Did you want to? If someone has a computer, they can Google.
that sucks.
What am I googling?
Oh, I'm pretty sure she died.
did-
She came back down.
Lucky survive or die in space.
'Cause
But what do you guys think of ethics in terms of having a dog up there?
It's fine.
if it lives, it's fine. Like if it's not hurt in any way or traumatized in any way,
It's
Go
okay.
for it.
Died during the mission stage.
I just don't want to be wrongfully
In
sad
the what?
today.
In the mission
It's
stage.
okay, Adam.
Okay.
Because if
Karen?
there's someone there to take care of the dog, then yeah. But if the dog's up there all alone, then it's like
Your
you
dog
can't
died
control the
within
aircraft.
hours.
Okay.
Yeah.
Apparently, it died within hours of takeoff.
That's just kind of sad. Like that's
Damn.
sad.
Carrie, what do you expect if you put a dog in
Terrible.
So would
You
it be
can't
better if you
steer
put a
the-
chimp?
The ship.
No.
You can't.
Yeah.
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 All right, Eli.
If it works.
I think
I
they
think
should have a
Said that.
place to take
The
care of.
first dog or whatever
I think that'd
died
be
within
easier.
hours.
Like, if you're
More than the
putting
Soviet
something
Union.
that can't actually
Or,
like consent to it in space, like
It wasn't
a
part
human
of
could be like, yep, like I want to go to space, but a dog can't say anything about it.
What other
Or it
animal
can go
you could say?
woof, a woof.
Parrots.
No, why would you think
What?
a dog would be able to live?
Okay.
Well, I
Send a
guess they were
baby
trying
into
to design a
space.
capsule that could support human life, but they didn't want to test it on a human initially.
Explosive.
But Eli makes a fair point in that dogs can't really consent,
It's like-
whereas humans can. Like an adult.
We have more humans than we have dogs. Just get rid of the humans.
I feel like you're making
Yeah,
a
dogs.
joke.
One human.
Just get like a
One dog will do a lot.
Okay, so we sent dog into space, and then after that, rocket sort of evolved. This is
Last one.
a rocket that is not really designed to go into high space, but it does go technically into space. It is a ballistic missile. And ballistic missiles, same as our rockets that send astronauts into space, are made up of the vast majority of it is fuel. So all this is fuel for the boosters. The payload is that little tip on the end.
Don't they have like 12 warheads
What's
in
in
that
the-
warhead?
What's in the payload?
Well, this one, who knows?
Okay.
That's a conspiracy. Because anyone recognize that dude?
Yes.
Kim Jong-un
It
knows
is
that.
him.
Kim Jong-un.
Yeah. So according to him, it'll be a nuke, but whether it's actually, we're not sure. So he's trying to show off his fancy missile. Whether what's in there, we're not entirely sure.
Trump and Kim Jong-un like shaking hands and stuff. And
Yeah.
it's not-
Yeah.
There's so many memes.
So they're gonna bomb Canada.
Really hit a
They're
kid.
really not.
Straight on.
All right. So here's a look at a space rocket. Space rockets are very clever in that they break down into sections. They're called multi-stage rockets. This stage here is the primary boosters. That does the primary takeoff, and then it drops away. And then these boosters here are inside the rocket. That will fire and drop away. The reason is because by the time these rocket boosters here use the fuel in the lower section, you don't want to be carrying this empty section of rocket that's heavy but has no fuel in it. So they drop sections off, and then this continues, it drops off, that continues, it drops off. These are the bits that just make it into space. So the vast majority of the rocket that we're looking at is actually designed to drop off and be discarded as they go higher. Yes?
So in the Apollo 11, like when they first landed on the moon.
Yep, this is the Apollo mission.
Okay. Like how when they landed on the moon.
Yeah.
How did they get back to Earth when they had like no fuel and stuff?
So I guess the fuel is required for two things. It's to fight gravity and fight the atmosphere, which is the friction. So that fighting up against Earth's gravity and up against the friction takes a lot of effort. But coming back is much easier because the gravity's helping and you're falling. So it takes very little fuel to fall into Earth. It takes heat shielding and good angling, but it doesn't require the same level of boost to get back.
Oh.
So, since the Apollo spacecraft couldn't be reused,
Hmm.
did they just build did they use the same blueprints and build like almost the exact same design with little revisions, or what did they do?
Yeah, basically. So that's why I guess these aren't great because you have to remake all new ones. But one of the benefits of the shuttle launch, and we'll have a quick video of the last shuttle launch, is that the components of the shuttle, remember the 2 booster rockets and the massive fuel tank, they were parachuted down and got to be reused. Similarly, we'll see Elon Musk's new sort of SpaceX launch, and that it is like very spectacular. But I'll see in a sec. But yeah, so we get to reuse them. Tom.
How does a single warhead have 15 different nuclear? Well, how does like one of those rockets hold 16 different nuclear warheads?
I don't know. It can be your question, but I'm guessing the rocket will deploy different payloads as it flies overhead. I don't know. I don't know enough about ballistic missiles. All right, let's watch this one. Come on, machine.
Make it quick.
Like a bad guy in a
No.
T-minus 5 minutes and counting.
Go for orbiter ATU start. GLC, perform ATU start. SRO. SRO, do you have a range clear launch?
This is Cape Canaveral where they launched from.
And entire crew is go.
Okay, Shooter, look, it's a great day to go fly. On behalf of the KSP Processing and Launch Team, I'd like to wish you, your crew, and the whole Hubble Space Telescope team a great mission. Good luck, Godspeed. We'll see you back here in about 11 days. Enjoy the ride, pal.
Also check that the SRB's firing chain is armed. Now suppression water system armed. T-minus 10, 9, 8, 7, 6, 5,
Just think about the amount of fuel that's firing out. So those are those side booster rockets falling away. And then eventually the fuel tank will fall away as well. It also has a booster on it.
nominal first stage performance. Atlantis is continuing its due easterly course to catch up with the Hubble Space Telescope one last time.
Epic.
Can we watch? What's the
Elon
one that
Musk.
crashed?
Can we
Or
watch
is
the
it
one that
that
exploded?
Challenger.
Can we watch Challenger
No.
lift off, please?
No, it's just normal. We don't need to watch Challenger. But, so you'll notice how, as they go up, the idea is to lighten the satellites as they, lighten the rocket as they lift. Turn.
How do they keep it like balanced that it doesn't turn when it's flying up?
Yeah, good call. So you notice how the shuttle has sort of wings on it. Those wings have flaps. That's what allows it to come in and land
Just
like
like
a
on
plane.
airplanes?
Yeah, just like on a plane. And my guess is they are connected to a computer and a gyroscope, and the computer can feel when the rocket is off course and make minute adjustments in the flaps. But did you notice how it went up and then appeared to turn? Yeah, we'll talk about why in a second, but first I'd like to look at SpaceX's Falcon 9. So SpaceX's Falcon 9 is a stunning rocket. It has quite a long section. The tip, once again, is the payload. The bottom 3/4 of it is the incredible part. It takes off, boosts up, but when it gets very close to space, the bottom 3/4 breaks away and then fires its engine again and lands. And the zooming in on the landing process is it, as a rocket, drops down vertically, initially over the sea, just in case things go wrong and they abort, so it lands in the sea. But if they're confident that everything is going well, the rocket flies itself down and standards itself back up on the landing pad, which is incredible. That they can just bring it back, refuel it, and send it up again with a new payload. Yeah.
What happens to the pieces that break off? Do they just fall in the ocean?
These bits here? I don't know.
Because they look
Probably.
like
They-
it looks like it has a little booster on it.
Yeah. So yeah, it does look like the second stage booster bit, the fairings, the bit that separates it, break off.
Are we gonna see a video of it?
Yeah.
Okay.
Yeah, they've done this, which is the incredible thing.
Come on.
Yeah.
Yeah.
Did you watch the live stream?
Yeah, last year
We watched like the
We watched the
landing.
live
SpaceX
stream
live stream
and,
because I got like
on
this little
YouTube.
subscription so I can see like all the live streams that will notify me like when it's gonna happen.
Interesting.
And
watch.
yeah, and he put it on the board, and we all watched.
Yeah.
Sorry, Eli.
It's kind of ironic because we're all trying to figure out a way for pollution, like how global warming and the amount of fuel and
Elon Musk in particular with Tesla, Tesla rather. Yeah.
is putting into our ecosystem is insane sometimes.
Well, you can't
Well, you
really
gotta go
boost
up.
the rocket any other way.
Well, yeah, I understand that, but like
He's like a giant
we're
angry
not gonna
bird
have it.
essentially.
Yeah,
Did you not hear that global warming was a myth?
Oh, they can't.
Guys. All right, let's watch how this works in practice.
In the background of the video, you see global warming's actually a myth.
T-minus 20 seconds.
Stage 2 tanks
Oh, and I should apologise that this does feel like a bit of a personal ad for Elon Musk. It's clearly partially PR, partially information, or partially like
Non-PR.
yeah. Thank you. Whatever non-PR is.
If you see anything on the sensors, that's a problem. Go say go for arm. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
This sounds good. You just kill the lights because it becomes rather an open black in a second.
Speed of 1.2 kilometers per second, average distance limit.
So I just want to pause to point that out. Speed bumped by 2 kilometers per second. And we'll talk about the speed required to get out of the Earth's gravity in a few minutes, but that is ridiculously fast. And that's not even the speed, that's how much things bumped by.
Shortly after the main engine cutoff, we're going to separate the stages and begin the second stage ignition.
Come on.
So the satellite is being deployed, but now is where that things are really impressive.
A series of 3 burns to head back towards Cape Canaveral.
Oh, the 2 pieces that break off, they also land.
Oh, where is it? Okay, this is bad. Potentially bad.
still landed back
We saw a smaller one.
there. It was like
Pardon?
We saw a smaller
Yeah,
one,
it was
but
it was
like
like
a lot
there was like
quicker.
6 of us in like Mr. Cherson's class during
Yeah.
lunch.
and we saw like the live stream of it coming down and like stopping.
I think there was 3 of them that landed on the same platform.
Yeah.
But that is stunning, isn't it?
Yeah, it's
It's
insane.
crazy.
They basically run outside to have a look at it, so we don't need to watch the rest of it. But sorry.
Is there any reason they did it at night?
It's a good question.
They also like temperature wise and like temperature
I've seen
wind.
it done in the day. I was in Cape Canaveral in 2006 when one went off, but it was midday.
Yeah, I think they wait for perfect conditions, and quite often you hear astronauts getting frustrated because once they get in the suit and all kitted up, they then have to sort of wait, and if the atmospheric conditions aren't perfect, then they get told to stand down and we'll try again later. And I guess it's that. It might also be that they want their satellite they're deploying in a particular pattern in the orbit of the other satellites, so they have to wait for the sort of gap that they want to slot it into so they can go off and push it in. But note how it also appears to go sideways towards the end. Alright, so what I'd like to look at now is why the rocket goes up and then sideways so much. And note the timing here. That is t plus 300, t plus 400. Do you know what those t's are? Time, good. So they have t take 1 or t take 10, and then they start that 10-second countdown. The first ignition and takeoff is the 0 point, and then it flies. And after 3 or 4 minutes is what these things happening, and second stage engine cutoff is t plus 9 to 11. So the second stage engine cutoff is, 9 to 11 minutes after we've taken off. So the video's compressed everything a little. But let me just flick all the way through to here. Now, orbit is a bit of an odd concept. We'll watch a video, the first 2 minutes of it. The guy has an accent, but try and get past that. The other class kept laughing at it. In order to escape Earth's velocity, escape Earth's gravity, you must reach what's called escape velocity. It means that your speed must be 8 kilometers per second. In terms of speed in kilometers per hour, that's 29,000 kilometers per hour. So escape velocity is the speed required to leave the Earth's gravity. It's not the speed required to orbit, but it's enough to get out if you're planning to go to the moon or send a probe off somewhere else. You must be going at least that fast. And well done for those of you guys who noticed we've hit the first section in the notes. Describe what is meant by the term escape velocity. So escape velocity is the speed required to escape Earth's gravity. And I flick this.
You must have seen GPS devices used in cars.
Yes.
It helps us to reach our destination. But do you know what helps GPS in navigation? Artificial satellites orbiting in circular orbit around the Earth help us in GPS navigation. Have you ever wondered how do artificial satellites get there and stay? Let's find out. In the universe, all objects having some mass attract each other due to gravitational force. Now, if the object is projected with some horizontal velocity, the object will follow the horizontal path initially, and then due to gravitational pull of the Earth, the object finally falls on Earth's surface.
And you'll all have seen this at ground level. If you throw something horizontally, it'll go flat for a while, but eventually it'll go into the ground. If you go somewhere exceptionally flat like Saskatchewan and fire a bullet, it will go flat for a really long time, it appears, but slowly it'll curve down and hit the ground. So that is what's happening on ground level. Same sort of thing applies when we're higher.
On increasing the magnitude of horizontal velocity, the object will drop a further distance apart. Now let's use a machine which can project the object with such a high velocity that it follows a circular path around the Earth.
So it still falls, fires out and falls, but weirdly enough, keeps falling.
This horizontal velocity at which the projected object reaches its orbit is known as orbital velocity. This principle is used to launch a satellite on its orbit. During the launch of a satellite, the rocket first reaches to a suitable height above the Earth's surface, and then it projects the satellite horizontally with orbital velocity. As a result, satellite orbits around the Earth in circular orbit. Let us now look at the...
Let's look at the math behind it. We're not going to look at the math behind it, but the important thing to recognize is that in space, you're not so much floating. So when we watch Gravity and Rhinestone is sort of floating up in space, she's not stationary by any means. They're going incredibly fast. They are going fast enough to orbit, effectively fall around the world. If they slow down and stop, then they fall into the world, which is the re-entry part. And that is, I guess, why you'll see all the rocket launches go up and then appear to like veer off course sideways, but they meant to do that. In fact, they have to maintain orbit.
So when you're in the orbit and you're going around, that's like you're getting faster, right? Like, can't you use this like a slingshot?
So you can use this as most.
Did you not see the Martian?
Most satellites in orbit remain at a relatively constant speed. If they go faster, they end up swinging out and getting a larger orbit, or if they go faster altogether, they swing out and go altogether. But you'll notice that if you look up, say, the Voyager probe's path, they sort of use planets as gravitational slingshots. So they'll be sucked in by the gravity and then get to pull around. So yeah, we certainly can use the gravity to help slingshot our probes further out. We haven't done it with people yet, but yeah, it's certainly a concept we can use.
Could you, so say we fly, so when we flew the Apollo 11 to the moon, was it a straight course, or did we use gravitational assist around the Earth to slingshot us to the moon?
Excellent question.
I
don't know. You'd have to Google the path of the Apollo 11 mission. But yeah, it's interesting to see if they were to go straight, or if they'll go up into an orbit and come around and go out.
I'm pretty sure they went into orbit.
And then
I actually don't know. But yeah, it's a good question. No, I'm sorry, I don't know. But yeah, by all means, look it up and then tell the past, because that would be a brilliant one to know. Alright. So the rockets we've seen so far have been powered by chemical propulsion. And the vast majority of the rocket is a basically storage area for those chemicals. And it's a mixture of kerosene and liquid oxygen and liquid hydrogen. Basically stuff that burns incredibly highly. It's hugely flammable. And it's relatively expensive stuff. To get liquid hydrogen and liquid oxygen and kerosene all mixed together in the right mix costs about $450 million per launch. So that's not the equipment, that's the cost of refueling the vehicle just to get it up again, which is a lot of money.
What is the payload of the vehicle?
Don't know. I guess a satellite, but I don't know how many kilos. The rule of thumb is that each kilo launched into space takes 10 to 15 kilos of fuel.
No.
If that kind of makes sense.
Don't they have multiple satellites per each one too?
Small ones, yeah, if they're going with probes or smaller satellites, they could. Dale. Yeah, go for it. Alright, so here's a PAT practice question, which I don't actually think is on the back of your sheet or anywhere on your sheet, but if you did get this in a PAT, you'd be pretty happy with them. Space shuttle is propelled into space by, which one? A, yep, chemical propulsion. So currently, chemical propulsion is the only game we have really to get ourselves up into space. Nuclear propulsion we looked at briefly last lesson, which was the idea of firing off nuclear bombs behind a craft, but it's been sort of ruled out for now anyway as unfeasible and likely to kill whoever's on board. But the next two we're going to have a little further look at: solar propulsion, ion propulsion. So solar sails act like sails on a boat, except they work using photons from the sun. So photons are like little light particles, and weirdly enough, when they hit, they have some momentum. So we don't feel ourselves being hit by the sun because it's so light compared to us, but it does still have some effect. It would be like a really, really light breeze. And the Japanese have figured out how to use this in space with a working spacecraft. And I think there's a picture of it. So this is their Japanese that's the Japanese spacecraft there. That basically extends out these sails and uses the solar power to catch that. Yeah.
What's an advantage and a disadvantage?
Good one. Okay, we'll watch the video and that will certainly flag some advantages and we'll think of some disadvantages also.
What if I told you our ability to travel faster and further in space was on the verge of a major breakthrough? That we could reach spaces we never thought possible over the course of a lifetime? Well, we may be able to do all that soon with the help of sails. Solar sails. To us on Earth, objects in space can feel like a cookie jar and a high counter to a kid. With current technology, chemical propulsion, a rocket can travel approximately 24,000 miles per second. Fast, but not fast enough. At 4.37 light years away, Alpha Centauri is the next closest star to our sun. With our current technology, that trip would take more than 100,000 years.
So, yes.
So if we sent people theoretically to that star,
Yeah.
and they survived to get there, but instead we sent other people, more and more people, as our spaceships got faster. So theoretically, that means that they could. What happens to people?
So I think right now with the rocket or chemical propulsion, we'd take, as you said, about 100,000 years to get there, which is insane.
What if we send more after we send
In faster craft, I guess they'd catch them up, wouldn't
No, or get past them.
they? Or pass them. You hope they pick them up for a lift. Keaton.
They chose that planet because it's like the next sustainable.
It's a sun.
Oh.
So Alpha Centauri is a star, but it has planets around it that we're interested in, and more importantly, it's the closest star to us. It's still like a long way away, but it's the closest to us.
Closest.
Solar sails
Stars.
theoretically can make that
Other than
trip
the sun.
in 20 to 40 years. That's night and day. So how?
So, with these technology, they're predicting 20 to 40 years, which is much nicer than 100,000.
But why do solar sails work? I asked Les Johnson, who's the lead scientist for NASA's NEA Scout project.
A solar sail is basically just like a sailing ship from the old clipper ships that you see in the movies, but instead of the physical wind, a solar sail in space is a sail that reflects sunlight. Most people don't realize as the light reflects from you, it's actually pushing on you. And that's because light doesn't have rest mass, but it does have momentum. So if you think of particles of light, photons, sort of like little BBs hitting something, and as they bounce off, they give a slight push to it.
The point is, if you stick a light enough and big enough metallic sail near the sun, away from Earth's gravity, it's gonna move.
As you get closer to the sun, you get a lot more push from the sail. If you cut the distance in half, so you go halfway toward the sun from the Earth, you don't get just twice as much light on the sail, you get 4 times the amount of light. It's called the inverse square law. And unfortunately, the opposite is true. If you go out, you get a lot less. By the time you get out to Jupiter, you're getting about 4% of the thrust that you get at the Earth.
So what would this mean for missions looking to go far away from the sun, like an interstellar trip? Just open the sail up for business close to the sun. From that initial push, you could just coast and still move faster than a rocket could get you going.
So you're sort of visualizing their plan. Clearly you need the sun's power. The closer you are to the sun, it gets much more powerful. Their plan is fly using regular propulsion closer to the sun, open up the sails, and use that as a push. And because there's no friction in space, that push will never slow down. You've just got to keep going until, well, either you slow yourself with thrusters, or I guess you could use gravity of somewhere else to slow you down.
How are they gonna get it like off of the Earth? Like, would they still use the chemical rockets and just and kind of like a shuttle where it's riding onto the chemical rockets, and then when the rockets drop, do they just use the sail?
Yeah, so that's a massive disadvantage of this system. You need to use the chemical rockets. It's not enough on its own to get out of our atmosphere. You'd have to use it in partner with other technology, say chemical rockets. Come on.
What about space debris?
Yeah,
Can't they just like
puncturing through the sails?
Like wouldn't it rip like the sails apart?
Yeah, so that's another, I guess, downside is they're fragile. And you'll see a picture of the sails in a minute. They're incredibly fragile. They are...
Super wide?
Yeah, super wide but super thin. They are a quarter the thickness of a garbage bag. So if you imagine the thickness of a garbage bag, like the plastic in your garbage bag, a quarter that thick is how big they are. So yeah, they're very fragile.
The fact that light pushes objects has been known for quite some time, but the fact that it could be used for propelling a spacecraft wasn't discovered until the Mariner missions, which was a bunch of probes in the 60s. One of them had a failure and tilted. NASA scientists figured out that they could use sunlight pressure to right the ship. Now, the Japanese were the first to use the sail in a mission designed to leave Earth's orbit. Their Icarus mission took off in 2010 and successfully used the sail to take a peek at Venus. Now it's NASA's turn. Enter the Near-Earth Asteroid Scout mission. Several branches of NASA are working on it. The mission's agenda is in its name. They want to send out a bunch of small...
Question. If the sun is pushing you away, and they use the sails to go to it, how are they going to it if it's getting pushed away?
Good question. My guess is that once they've got enough push from our sun, they'll pull the sails in so they don't get stopped while going towards the other star. As in, but
if it comes out from Earth and it wants to go, Venus is like the sun is here and the Venus is here, right? How did it get here with the solar setup?
Maybe they left it hanging in space until Venus's orbit came round and they could be pushed, like Venus would be directly out from the sun.
Oh, yeah. Okay. I guess. Yeah.
Did they put people on the solar sails of Venus?
No, it was just a little probe. And same here, they're only talking about tiny things.
All robots to check out nearby asteroids to see which, if any, are worth a closer look or a potentially manned trip. The plan will use sails about the size of a school bus to help the robots pick up speed that they otherwise would not have, by a factor of about 3 miles a second. It's a humble start for what this technology could ultimately grow into. And grow they'd have to. From a school bus-sized sail to something hundreds of times bigger.
That is a picture of the probe and sail they're planning to send out. So in this case, it's tiny, and that is very, very thin, but what they're saying is it's a start, and that this technology can be scaled up, in theory. Yeah?
It just looks like tinfoil.
Is the probe, like, emitting radiation? Because, like, why are they wearing those suits?
Because I don't know.
Oh, it's like
It's really
dust, like fabrics, not to...
Yeah, I'm not sure. You'd be pretty nervous when you're kneeling there with that stuff that thin. Like, sorry, Tara, did you have a question?
Yeah, I think it's just so they don't contaminate it and possibly damage it.
Yeah, fair. I'm supposed to check my phone.
Can you imagine NASA's enacts like you break it, you pay for it?
I'm sure they don't.
Sail to something hundreds of times bigger.
This technology is really scalable. And in the far future, it's going to be one of the few technologies that might enable us to actually send robotic probes to another star. Now, we don't know how to do that today. The technology is not here. As a physicist, I can tell you that it should be possible. And with materials that have come along, things like graphene and other things, I think we're on the edge of having a breakthrough in making really lightweight, really efficient sails. And it won't happen in my lifetime or your lifetime, or probably not in your viewers' lifetime. But I think within the next 100 years, we're probably going to be able to use this technology to take big steps beyond the edge of the solar system. And that's what excites me.
The obvious question now is, where to? If we could use this technology to take the jump, where should we go?
The dreamer side of me would say, let's send them everywhere. The person who knows that somebody has to pay for it, wants to get the data back, and doesn't want to take too much risk, I would pick the easiest low-hanging fruit. I'd go to the closest destinations first.
Although the bigger jumps will likely happen without us seeing it, there are things that could happen with this technology that would be very exciting in our lifespan. NASA is looking at sails to take a craft into interstellar space 5 or 6 times farther than where the Voyager crafts already are. If we're that kid reaching for cookies on a high counter as far as space travel, we're not there yet, but with sails, we may have just found a chair to help us reach a little higher.
Oh, God.
Can I just ask?
The deep end
Why do they use the railgun to shoot the little probes in space?
Yeah, possibly. I guess railguns don't work with people because the acceleration kills us.
Yeah.
But they've looked at it as a theory for the probes, I think.
Well, wouldn't, since you were saying that the solar sails are really fragile, wouldn't the railgun not work? Because since it's being shot out at like such a high speed.
I think they're planning to like, did you remember how the Japanese one sort of spun and then the sails came out? Maybe you could like pack them in nice and tight and secure them. But yeah, I think the ridiculous acceleration in a railgun probably still is an issue.
Either way.
Pardon?
Either way, they're going the same speed, like chemical rocket or railgun.
But the acceleration is very different.
Oh yeah.
But yeah, you're right. They do get up to the same speed, just the acceleration is a different one. Sorry, did you have a question, Adam?
Yeah. What if they were to launch like a railgun in space that would orbit, kind of like the telescope, and they would send cargo up to it and then shoot it, because then there would be no G-force on the substance that's in it?
There's still G-force. G-force is how you feel the change of direction.
Oh.
So it's like, you know how if you're, well, let me say, in your mother's car when she slams on the accelerator and you feel that, because it's a Subaru, it can do that. That's G-force on a very low level, and it's not to do with gravity so much, it's with the fact that you're accelerating.
Yeah.
And yeah, I think you would still feel that effect in space.
But wouldn't it be like a lot less?
I don't know. No, it's still acceleration.
It is accelerating.
I know you wouldn't have the element of gravity pushing down, but you'd still have that acceleration going forward.
Like the resistance. So technically you could go that way for a long time.
Yeah, because nothing's stopping you.
If it was very long and powerful like the ones we have on Earth, if we just had it orbit and then shoot up like little things, you just shoot them off.
Nadine?
What's 3 and 4?
We have 4. So, what are advantage and disadvantage of solar sails? Sorry, Tyler.
Sorry if this is already said, but like, why do they have to be so big?
Good question. Any guess on why it has to be so thin? Maybe because it's light. But you're right. I think. Actually, no, I do know. It's because they want to conserve weight. I think. Imagine, say you're standing on a skateboard, and Jackson gives you a push. You'll go a certain distance. If I'm standing on the same skateboard and Jackson gives me the same push, because I weigh more than you, I'm not going to go as far or as fast. So I think there is sort of motivation here to keep the weight low so that any push they get will have more of an effect. But yeah, that's it. Sorry, Nadine. So advantage and disadvantage of solar sail. Disadvantage is we can't use it to escape the atmosphere and the technology isn't there yet. Advantages are it is potentially quite exciting. We can move potentially very quickly. And it's, I'm sure we'd agree, an environmentally friendly way of doing this, because we're not taking up a massive amount of chemical fuel into the sky. Alright, second future tech we're going to look at for a little bit is called ion thrusters. And they sound like something out of Star Trek, but they exist and we have them working. They run on something called xenon gas. And xenon gas is a type of noble gas. Have you guys done much looking at the periodic table?
No.
Okay, well, I might just bring up an image of it.
Did we start that this year?
We do start that this year.
Can we mix actual elements together?
Hey Jackson, going to Aspen?
Are we there?
Alright,
Hey, Keith, you gonna ask me?
so this is the periodic table, and each of the elements or coloured sections has special properties. So, for example, the fun ones, if you Google these guys, lithium, sodium, potassium, etc., being dropped in water, you get to see some great explosions. They react poorly with water, they blow things up quite well. These ones are kind of boring, they're like the metals. But these ones over here are interesting, and that's xenon, what ion thrusters are currently powered off. And this blue group here are called the noble gases. Yeah, Dan?
What's the deal with like the other elements on the very bottom being separated from the rest?
Well, I think it was good when we originally drew up the table, we discovered these, and then we realized these guys actually fit in there. But if we slot them into the table looks really long and ridiculously thin. So they're really just like, they live in there.
Oh, because they have a little dust.
Yeah, that star fills these guys in that one and there and there. Come.
What makes the biggest explosion on
Of course, Colin would ask.
Is that hydrogen on top in yellow?
Yes. What just happened?
Can
Pardon?
I buy translucent?
No, it's very unstable and only exists for a couple of seconds.
Which ones can I
You could probably buy sodium. Oh. You're scaring me now, Colin. No, tell it. Alright, but these guys here are the noble gases, and do you guys know what noble means outside of, I guess, science? Like if you were talking about someone who is a noble in social studies, what sort of people do you talk about?
Oh, like a noble.
Good, knights and kings. Yeah. So in older times, the nobles were the ones who owned the land. They were the knights, the kings, the lords. They owned all the land, but they didn't actually farm it. Other people did that with them. And the scientists named these noble gases, and the nobles were quite honoured. They're like, great, a whole group of things have been named after us. But the interesting thing about these guys is, while these ones explode, these ones do nothing. They don't react with anything, they don't explode, they literally do nothing. So naming a group the noble gases is naming the group that does nothing. So it's actually kind of like a mini insult to the nobles. Which is, yeah, scientist's idea of a joke, I guess. Ion thrusters. The good thing about ion thrusters is that they're incredibly efficient in terms of fuel load. So for every 10,000 kilos of rocket fuel, you only need 860 of xenon. The downside of them is that their thrust is incredibly low. So their thrust is 10,000 less than what rockets are. So once again, these guys are not going to get us out of the atmosphere. They'll only be used once we're already up there. However, they can pick up to very high speeds, and they've been shown to run consistently over several years.
Does it cost a lot of money?
Everything in space does. I'm guessing so, yes.
So
But I don't know. Yeah.
So the thrust runs on xenon?
Yeah, and it's sort of a gas. But the actual how that happens, they'll try and explain in the video, but you don't need to know in great detail.
Ran NASA's Breakthrough Propulsion Project. One of its long-term goals was to move away from using rockets. The problem with rockets is not that they can't beat gravity, it's the amount of thrust they need to do it.
If you think about the Apollo spacecraft, and you imagine here's a Saturn V, the very tip of that and then a little bit below that was the actual spacecraft itself, and all the rest of this was the propellant, the rocket fuel, and that's just to the moon.
At the Glenn Research Laboratory in Ohio, work is underway to produce new forms of space engines. Ones that really could take us where rockets can't, beyond our solar system.
What we have here is a high-powered ion thruster, and the way it produces thrust, our ions are created inside this ring, and then we establish electrostatic potential that accelerates these ions out and produces large velocities. And what that does is it gives us very efficient production of thrust.
This is an ion thruster under test, pouring out a constant stream of charged particles.
So it does look very Star Trek-y, but they're powering it with light, or particles. So atoms all have a whole bunch of neutrons and protons inside them, and electrons. And we'll look at this more in sort of physics, but the protons are called positive and the electrons we call negative. If you rip some of the electrons away, the balance shifts and the whole thing gets positive. And what they're doing is they're creating ions, and ions are atoms that have a charge, so in this case probably positive, and then they create some electrostatic potential here, making basically that giving this area a charge as well. And you know how if you push your two edges of magnets together that are both like north ends and they bounce off? What they're doing here is they're charging particles, say ripping electrons from them, then charging the center to have the same charge and then boosting it away using that same sort of process.
Let's drip.
Which is very, very clever and cool.
It's less powerful than a rocket, but capable of accelerating a spacecraft almost indefinitely.
These systems are ideal for in space. You know, we operate them purely in space because it's very gentle. You know, the thrust level is low, but over time you can develop much higher velocities than you can with chemical rockets.
So, those are the three main propulsion systems that we're seriously considering. Chemical, which is so far the only way we've figured out getting out of the atmosphere, but then solar sails and ion thrusters. Alright, so, satellites. There are two things you need to know about satellites. Well, and it says here what is the difference between an artificial and a natural satellite. And, not surprisingly, natural satellites are ones that we did not put there. They are moons, they are the asteroid belt around Saturn, they're anything that orbits another object we call a satellite. If we didn't put it there, it's a natural satellite. However, artificial satellites are the things that we put there. And this is a quick map of some of the satellites above Earth currently. We're going around crazy flying. Okay. And I think that's quite an intuitive sort of balance between them. Flicking on. So artificial satellites hit a lot of different boxes in terms of helping us in our daily lives. They allow GPS to run, and then they allow mobile phone communication, weather monitoring, land survey, presumably some spying.
And how much satellites do the three?
Yeah, so what you use quite often in your phones is GPS. And GPS is a bunch of basically located satellites in the sky, and your phone will basically look at them and ask what direction are they in, and for that they use a process called triangulation to find out where you are. It's a bit like if I want to know where I am in the room and I use the three heads of the table, Kerry, Dale, Chase, and to figure out where I am, I can draw a line between the three of them, and where that line meets is where I'll stand. Or if I'm over here, the line from the three of them changes, but I can still imagine a line meeting somewhere in particular. So if I know where they are in the first place, I can draw a line back, and that's where I'll be. And that's kind of what your phone does. It needs a minimum of 3, but in reality your phones will often grab far more than that. They'll link on to sort of 17 or 18 up in the sky. There are a couple of different ways the satellites orbit. There are the polar orbits, which unsurprisingly go over the poles. And there's another one that's quite interesting called geosynchronous orbit. If you break down this word, can anyone sort of take a guess of what it means?
Geo is
Earth. Good.
Sync is going with something being in something. Chronos is
Nice, Colin. Sorry, Colin had it. In that geosynchronous, synchronous is to synchronize, or same time, chrono meaning time, sync, so same time with the Earth. A geosynchronous satellite will stay in the same position above the Earth all the time. So as the Earth rotates, the velocity of the satellite has been rigged to match the same position above it. So it will fly, keeping in line with the same position of the Earth. Yeah.
Why is there this is kind of off topic, but
It's alright, yeah.
thing. Why is there nothing specified for nothing around the Antarctica? There's no humans on it and stuff. What is Antarctica?
So weirdly enough, the
Is it
No, it's real. The Arctic at the north isn't technically land, which
It's
sounds
just ice.
it's ice, quite heavy flows, but in theory,
Antarctica is land, isn't it? We're covered in that.
there's some islands, but you can sail a submarine under the North Pole, which is pretty cool. But in the south, the Antarctic is actual land.
So is Santa real?
Are you still
Santa's
still not coming down on that? Huh?
Santa's dealing with flooding issues.
But sorry, Jackson, what was the actual question? Why does no one live there?
No, it's
Oh.
Nobody ever. If there's land, it's why does nobody ever talk about it or do anything about it?
I guess it's interesting. It is the only major piece of land that had not naturally inhabited. So even parts of the Arctic region, the Inuit people will have made their way into an inhabited. But when, I guess, explorers discovered Antarctica, there was no one living there. It was truly terra nullius.
Jackson, why would you just
screen?
Nadine.
I'm just thinking because
Yes,
and
Nadine, can I
like
help you?
why do they want to like set a military in
good.
the Arctic but not in Antarctica?
Okay.
So I guess for Canada, the Arctic is quite a strategic zone because it would be a very quick and easy way to get to Russia or even China over the pole. So if there was any conflict, part of the defences will have to defend that top area. But and for whatever reason, I'm not sure, but most of the world's powerhouses are in the northern hemisphere. So that means the Arctic, which is top of the northern hemisphere, is quite strategic. Antarctic, I'm sure, has some strategic value, but you don't have Russia, America, China on the doorstep of the Antarctic. It's Australia and New Zealand and Argentina down there. Like it's
Military there. They don't tell anybody.
maybe. Sorry, David, you had your hand up for a while.
How many satellites are in Earth's orbit right now?
I have no idea, but a lot, like a high number. I don't know.
Oh,
No,
it's
you're
like
damn right at
24
the
and
end.
it grows.
Santa.
No, it does.
Wait,
This is and Mr. Claus.
So like, if the North Pole is real, then does that mean Easter Island is real?
Yeah.
Right.
Whoa!
Where is Easter
Island? So epic.
There's an island called Easter Island. Alright, so have a look at this PAT question. And so read the question, imagine highlighting some key words in it, and then try and imagine the correct answer. I haven't taught it to you explicitly, but try and think about, I guess, what would be logical. And the question is, which pair of satellites in the diagram above can transmit signals over the greatest area of Earth's surface?
Why?
Satellite W.
Y and
I
W.
can see X, Y, Z, but why W?
Alright, good. Y, and W. Is the correct answer. The correct answer is Y and W. But why them?
I feel like this space in between.
Good one, Taran?
It goes up and over mine.
Well, I don't know if this is right, but they just seem the farthest out.
Good.
You like
Yeah, absolutely. They are the furthest out. And it sounds odd, but if you grab something cylindrical, or even like a soccer ball, I don't have one, but this will do. And if you look at it from a long, long way away, you can see a fair part of it. You can see almost half of it. But if I hold it really, really, really close to Adam's face, he's not going to be able to see as much of it. Sorry. Like, the thing is, the closer the satellites are to the surface, the less area they can broadcast over. Whereas the further out, they can broadcast over a much further area. There you go. Thank you. Okay, what I'd like you guys to do now is, can you turn over and have a look at the questions on the far side? Probably end this recording. It is 10:30.
Well.